This is our video about Chapter 12, which is solids and modern materials. We're going to review what it means to be a solid. We're going to talk about crystalline structures and some different types of crystalline structures. And we're also going to talk about types of solids. When we describe a solid, we usually say that solids tend to be the more dense of the states. The particles are more closely packed than other liquids or gases. And we also say that the kinetic energy tends to be the lowest out of the states of matter. Now, even with those descriptions about solids, there can be some differences in the way that that works out. Two ways that we can describe solids are either crystalline or amorphous. Crystalline means that there's a well-ordered and kind of repeating pattern of molecules or atoms. The structure is very defined there. In amorphous, the molecules or atoms or ions, they're just kind of laying on top of each other like a pile of atoms, and there isn't a specific structure. Now, within crystalline solids, we have kind of a selection of different things that would make those crystalline structures. If the crystal is made out of positive and negative ions, we call that an ionic crystal. And that kind of goes back to our talk about like crystal lattice structures and ionic bonding. If the crystal isn't made out of ions and it's made out of molecules, it would be a molecular crystal. An example there would be something like water crystal, which would be ice. If the crystal is made out of metals, those are just metal atoms stuck together. So an example there would be just like solid iron. And this last one that's on the list here, network, sometimes we call it network covalent. It's a crystal made out of covalent molecules, and those covalent molecules are held together by covalent bonds. And these are really interesting crystalline solids. They're kind of like an in-between ionic and covalent with their properties. A good example here would be something like silicon dioxide, which is what quartz is made out of. Here we have a schematic that kind of shows the variations in crystal solids. So all these things are crystalline solids. They are separated by what the kind of smallest units are. So molecular solids, the smallest unit is a molecule. In an ionic solid, the smallest units are cations and anions. And in an atomic solid, the smallest unit are atoms. And what I like is across the bottom here, it has examples of each type of them. Now, another way that we can describe crystalline solids is what the crystal itself looks like. So I'm just going to use this solid xenon picture as an example. It's just xenon atoms stacked together, but depending on the spacing between these xenon atoms and how they are packed together, the crystal can take on some different properties. And so I kind of want to look at what it takes to measure that spacing between atoms, and then talk about how different spacings and different arrangements give us different kinds of crystals. So how we measure the spacing between atoms is we use this technique called X-ray crystallography. Now, kind of really simply, how an X-ray crystallography instrument works is they use an X-ray source and they basically make an X-ray laser out of it. So that's called collimation. They just kind of control where the beam is going. And then they shine that X-ray beam on a crystal sample, and these samples are usually pretty small. And depending on what the spacing is between the protons in that crystal, the X-ray is going to be reflected in different directions. And so you get this really interesting kind of like spot pattern, and you can use like a photographic film to collect that. Nowadays, we actually use like a CCD, a charged coupled device. That's just like a fancy version of a digital camera. So once you get that pattern, they use the spacing of the dots and kind of how big some dots are and some little dots are. They use that spacing to figure out what the spacing was between the protons in that crystal. And depending on how spaced out the protons are, they can actually figure out what the crystal structure is. So they can figure out if there's some spacing, like this is one spacing, I'm going to call it A, and this is another spacing, B. If there's two different types of spacing, they can use the amount and how far those atoms are from each other to figure out what the overall crystal looks like. Is it what we call a simple cubic, or is it a face-centered cubic, or there's actually something else called a body-centered cubic? Those are the most basic ones, and those are the ones that we're going to be talking about. Now our job in this chapter is not going to be to interpret this information to basically find the type of crystal. That's very complicated, and that would be an X-ray crystallographer's job. Our job is going to be to take information that an X-ray crystallographer has given us, something like the distance between the atoms, is maybe something like 205 picometers. So they used an X-ray film to find that, and then we can use that information to determine what type of crystal pattern we have. And to be able to do that, to be able to make this step, we have to learn a little bit about the types of crystals that we commonly see. Now, when we say crystals, we're talking about something that has an ordered, repeating structure, like a pattern that happens over and over again. They are 3D patterns, so they're happening in the X, Y, and Z axis. We say that the smallest repeating unit of the crystal is what we call the unit cell. So the unit cell is the smallest representation that represents all the types of atoms within that compound. And when you stack those unit cells in 3D, so you stack them in the X, Y, and Z axis, you get what we call the crystal lattice. So that's kind of building a structure from a unit cell. The unit cell is the smallest, and the crystal lattice is what you get when you have many unit cells. So in nature, we see a lot of different types of unit cells. In this chapter, we are going to concentrate on the simplest of them, which is the cubic unit cell. There are 3 different types of cubic unit cells, and those are the ones that we're going to cover. What's nice about a cubic unit cell is that all of the sides have an equal length. So when we think about a cube, we're saying that this side and this side and this side all have the same length. The types of cubic unit cells that we are going to talk about are called primitive or simple cubic, body-centered cubic, and face-centered cubic. And we'll go over what each one of these looks like. They look different, and they look different because they have a different number of atoms per unit cell. The primitive only has 1 total, the body-centered has 2, and the face-centered has 4 atoms per cell. So face-centered has more atoms per cell than the primitive or simple. So let's start on the primitive or simple cubic. In the primitive or simple cubic, there is just 1 atom on each corner. Okay, so this is the structure here. And the reason why we say that there is only 1 atom in this unit cell is if you cut this cube and you only took what was on the inside of the cube, you would get 1/8 of an atom right here, you'd get 1/8 of an atom right here, 1 on this corner, 1 on this corner, and then on the back side, there'd be 1/8 in here, 1/8 in here, 1/8 in here, and 1/8 on this corner. So there are 8 times 1/8 atoms, and so you get a total of 1 atom that's on the inside of this cube. And you can see that kind of here where they actually did cut off the edges, so you can see all those little 8ths. If you move to this side of the screen, this is what happens when you take a unit cell. So this is our unit cell here, and you start to add one in front of it. So I'm putting a 1 in front of it, and you start to put one down here. So that's actually the same bottom, so I'm doing it like this. Okay, so what we're doing here is we're taking a unit cell and we're making a crystal lattice. So we're basically just building a 3D structure out of our unit cell. Now something else we can see in this picture is what we call the coordination number. The coordination number is how many atoms an atom from my unit cell is in contact with. And one of the best ways to see this is if I take my unit cell, so I'm just going to look at this picture here, and I'm just going to talk about this atom right here. If I look at where that atom is on my unit cell right here, it's this atom. Okay, so I'm going to clean that up, and I'm just going to mark that atom again. It was this atom right here. I'm going to look at how many other atoms that atom is in contact with, how many it's sitting next to. So it's sitting next to this one on the top and this one on the bottom. It's sitting next to this one in the back, this one on the side, this one coming out front, this one going to the left. So that is 1, 2, 3, 4, 5, 6. Every atom in my unit cell is in contact with 6 other atoms. Its coordination number is 6. So just to summarize simple cubic or primitive cubic cells, a simple cubic has 8 atoms. So these atoms here, 1 at each corner of a cube. If you count up just the atoms that are on the inside of the cube, so how many atoms are contained within the unit cell, there would be an 8th at each corner, so that means that 1 particle total is in each unit cell. I know that it involves the combination of 8 different atoms, but we only get an 8th of each one of those atoms on the inside of the unit cell. So the total there is 1 particle on the inside. The coordination number of each atom is 6. And I want to talk about this one. The edge of the unit cell is twice the radius. Let's look at a picture and see how that's true. So if we look at this picture up here, this is the length of the unit cell. So that's the edge. And because 2 atoms meet each other right here, the edge is equal to 2 radiuses. Okay, so if this is the radius of an atom, this is the radius of an atom, the edge is equal to 2 radiuses. And that's why we say that the edge of the unit cell is twice the radius of the atom. Now, why that little detail down here is pretty important is because you can find the edge of the unit cell. The edge of the unit cell is the distance between 2 protons. So we can find that by using X-ray crystallography experimental data. So we can find this distance, the distance between 2 protons. And if we know that distance is equal to twice the radius of the atoms, we can find the radius. So we can go from the edge to the radius. And what's important about the radius is that we can use the radius to find the type of atom. Remember when we talked about periodic trends and we talked about different atoms have different radiuses, things that are further down in the periodic table have bigger radiuses? And so we can actually now put some numbers on there. We can use a radius and match it to a particular type of atom. Now let's talk about another type of cubic cell. This one's called a body-centered cubic. It's similar to the simple cubic in that there are atoms at the corners of each of the cubes. But in a body-centered cubic, we add one to the center of the body of the cube. So the corner atoms are all shared by the 8 unit cells, just like they were in the simple cubic. But the one in the middle is completely enclosed inside the cell. And here we have a picture of what that looks like. We have the ones that are on the corners. So again, only an eighth of them is inside the unit cell. But then we have that one that's in the middle that is completely enclosed in the inside there. So when we cut off those edges and we look at what's just inside the cube, we see that there is 8 eighths. So there's 8 eighths. And then there's that one in the center, and so that adds up to be 2 atoms per unit cell. And so the body-centered cubic is actually more dense because it has more atoms on the inside of it than the simple cubic. Now in a body-centered cubic, we can't say, if we're trying to relate the length of an edge to the radius, we can't say that the edge is equal to 2 times the radius. That's not true for a body-centered cubic because you can see there's that empty space between the 2 radiuses. It's actually a radius and a radius plus some unknown value. But what we can say is if we look at the structure of a body-centered cubic, that if we go from this corner, so that's the back corner, all the way to this front bottom corner here, that is 1 radius. And then from here to here is 2 radiuses. That's a diameter of the yellow one. And then 1 extra radius. So that hypotenuse there is equal to 4 radiuses. And we can do some geometry to relate that hypotenuse to these other sides here because we know that it's a cube. And when that happens, we find that the equation that relates the radius to the edge is that the edge is equal to 4r divided by the square root of 3. So for a simple, the edge is 2r. For a body-centered cubic, the edge is 4r over the square root of 3. Okay, the last type of cubic cell that I want to talk about in this chapter is the face-centered cubic. The face-centered cubic, there are atoms at the corners of the cube, just like there are for the other ones, the simple cubic and the body-centered cubic. But in a face-centered cubic, there's also 1 atom in the center of each face of the cube. And when we look at that structure, it looks like this. So what we have here is we have ones that are on the corner, so an eighth of them is showing on the inside. And then these are on the face, which means that if you cut this plane, only half of them are inside the cell and the other half are outside the cell. So if we can look at it on this side, it's a little bit more clear. Because they're on the face, only half of them is on the inside of the cell, and you can kind of see it on this upper one. You can see the half on the inside there. So when we're talking about how many atoms are on the inside of a face-centered cubic, we have 8 times those eighths, and then there are 6 faces to a cube. Front, back, up, down, side, side. There are 6 faces, and each one of them has a half of an atom on it. So when we add those up, we get a total of 4 atoms per cell in a face-centered cubic. Now again, in a face-centered cubic, in all these structures, we're interested in how we can use the distance between nuclei, so that would be the distance between the middle of these atoms here, how we can use that information to figure out what types of atoms are contained within our unit cell, things like density, stuff like that. So we want to know how we can use this edge to tell something like the radius of an atom. For a face-centered cubic, the edge is not equal to 2r again, because there's that empty space. There's two radiuses and then this empty space. So we can't say that it's 2r like the simple cubic, but what we can say is that if we go on this diagonal here, so it's to this front corner. If you're thinking about what we just did for the body-centered cubic, we did from this corner to the back corner back here. That's not what we're doing this time. What we're doing is we're trying to figure out where the radius where the radiuses touch each other, where the atoms touch each other. So on a face-centered cubic, it's from this corner here to the front corner, and we can see that that is a radius, and this is two radiuses, and this is another radius. But because that is a hypotenuse, the way that the geometry works out is that the edge is equal to 2 times the square root of 2 radiuses. In the lecture slides that go along with this video, I've included some slides that are good review or kind of summary slides for the things I just talked about. They're also good for visualization if you're having trouble visualizing these cells in 3D space. I'm going to skip over them here, but they would be good ones to go back and kind of review if you're having trouble visualizing things, or if you wanted to kind of review for a quiz. Okay, and so I'm going to start back here. I think that this chart is a really good chart that summarizes the information about the cubic cells that we'll be talking about in this chapter. On this side, we have the names. We have how many atoms fit within one cell. We have the structure. We have the coordination numbers. And then we have the equation that relates the edge to the radius. So this would be that the edge is 2 radiuses. This is that the edge is equal to 4r over the square root of 3. And one thing that I just want to point out here is that on this slide, I feel like this equation, it seems clear, but just to be really clear about what it's saying, it's 2 times the square root of 2. Those should really be in parentheses and then r on the outside. A lot of people read that as 2 times the square root of 2r. That's not true. It's this one. And there's also something that I kind of just briefly mentioned, but we didn't put a number on it. It's this number over here, which has to do with density. So the way that it's described here is the packing efficiency. What that means is how much of the space of the volume of the cell is occupied by actual atoms and how much of it is empty space. So in here, if 52% of a cell is taken up by atoms, that means that 48% would be empty space. Okay, and you can see that as we go down the list, the packing efficiency for a face-centered cubic is much higher. It's about 20% higher. And that means that face-centered cubics are more dense, and the simple cubics are less dense. Now, different atoms form different types of crystal lattices. So there's not that many that form a primitive unit cell. So we're talking about pure elements there. The only one that we have on this list is polonium. A lot of our what we call money metals, which are kind of our precious metals, a lot of those make face-centered cubic. We have kind of in the kind of D block, we have some that make body-centered cubic. And then there's one that I haven't mentioned, and we're not going to do any calculations for it in this chapter, but I just kind of want to introduce it to you and show you what it looks like. but it's this one here. It's hexagonal closed packed, and I'll describe what that means. But we have a lot of elements. All these pink ones make hexagonal closed packed type crystals. So just going to show you some different options for stacking. We have two sets of oranges here. On this side, we have oranges that represent the simple cubic configuration. So in a simple cubic configuration, the oranges are stacked right on top of each other. And if you look at this picture here, you can see that there's a lot of empty space between those oranges. Okay, so if I were to put another layer of oranges, there'd be another orange here, another orange here, another orange here, but there would be nothing in that empty space between. So that's what we call a simple cubic. Once we start to fill that space, so once we actually put oranges between, so if this was an orange here, so once we start to put oranges between two oranges that are lined with each other, we start to fill up more of that empty space. And so this over here has a higher packing efficiency, and so it's more dense, and this one has a lower packing efficiency. Okay, so we've only seen the cubic one so far. I did want to introduce the hexagonal closed packed and kind of show you how that relates to these crystals. So here we can see that these marbles produce a six-sided shape around that center atom, and so that's what we call a hexagonal pattern. So let's make that into a 3D shape. And when we talk about stacking things to make a 3D shape, it's helpful to kind of label the layers. So what we have over here are some labeling of layers. And what this is telling us is that there is one layer with one orientation, and then another layer with a different orientation stacked on top, and then a third layer stacked on top of that. But the third layer and the first layer look the same as each other. So they're kind of like the same orientation of atoms, just in a different layer. And then the fourth layer is the same as the second layer. And so we call that an AB pattern. Just two layers. Each one has a different orientation, but they keep on going, layer A, then layer B, then layer A, then layer B. That's not the only option. We have other options like this down here. And on this one, we have one layer with an orientation, then a second layer, and then a third layer with a different orientation. And it isn't until the fourth layer that we see a repeating orientation. And so that's called an ABC pattern. And it works out that the AB pattern makes a hexagonal unit cell, and an ABC pattern makes a face-centered cubic. Now this might be easier to see if we can actually look at the 3D structures. So let's do that. All right, so on this side we have our AB pattern, and on this side we have our ABC pattern. And let's look at the difference between them. In our AB pattern, we have two layers that are the same. So the first and the third one are the same. And the one that's in the middle is a little bit different. So when I say orientation, I mean that the atoms are in a slightly different place. And how this works out is that if you sandwich these A patterns, so these A layers, on top of the B layer, what happens is that the A atoms nestle down in these little areas between the B layers. So this one's coming down here, and this one's coming down here. And then this A layer that's coming from the bottom side, they nestle down into the same little divots just on the bottom side. So it's kind of like the A's are oriented exactly the same, and the B is just offset a little bit. And so when we sandwich them, the A's line up, and they line up so that they are putting their atoms right in these little open areas of the B pattern. So when we do that, when we sandwiched one layer that's different between two layers that are the same, we get what we call a hexagonal closed pact. But if we use 3 different patterns, so here we have an A, a B, and a C, we get a face-centered cubic. So let's kind of see how that's different. So it starts off the same. We have an A pattern, and we kind of sandwiched it on, or we put it on top of a B pattern. And what happens is the A atoms nestle down into the divots right in here of this B pattern. So they're kind of right in there. But when we put the C pattern from the other side, because of its spacing, because it's moved, the orientation's moved just a little bit to the side, these atoms don't nestle into the underneath of the sites that the top atoms nestle in. That doesn't happen. What happens is that they nestle a little bit off to the side. And so there's the same amount of nestling, it's just that where the A pattern nestles into the B is not where the C pattern nestles into the B. Now what's really interesting about this is that because there's the same amount of nestling happening, but the patterns don't line up as well, what happens is there's the same packing efficiency. So they both have 74% packing efficiency, but you get different looking crystals. So let's get to some practice with some actual numbers. In this problem here, it says that silver crystallizes in a face-centered cubic. So we know some things about a face-centered cubic. We know that in a face-centered cubic, there are 4 atoms per cell. And we also know that the edge is equal to 2 times the square root of 2r. And so it says that each side of the unit cell has a length of this, so that is the edge. What is the radius of a silver atom? Right. So this is pretty straightforward. We know that 409 picometers is the edge, and we know that that is 2 times the square root of 2r. So if we divide both sides by 2 times the square root of 2, when we do that, we get 144.60. This, because it's geometry is exact, and so the only sig figs we have is this, which is 3 sig figs, and so I'd say 3 sig figs. I'm going to round up because that is more than 5, so I'd say 145 picometers. Now just a little plug here, if you're not super familiar with picometers, picometers are 1 times 10 to the negative 12 meters. So 1 picometer is a very small portion of a meter. Again, another way you could write that is 1 times 10 to the positive 12 picometers is equal to 1 meter. Either way you write that, it means the same thing. Picometer is going to be something that we hear about pretty commonly when we're doing cubic cells or any crystal cells, because picometers tend to be about the order that the edges tend to be on. So we're going to see some of these metric units that we maybe haven't seen as much before in this chapter. Now I'd like to do a little bit more of a challenging problem. This is a problem out of our course pack. It's on the worksheet called Cubic Cells 1. So you can turn to that in your course pack if you have it, and if not, we have the problem here. And this problem says that we are going to determine the radius of an aluminum atom in picometers, and it gives us a density, and then it tells us that aluminum crystallizes in face-centered cubic structure. So when I organize that data, I'm just going to say that the density is 2.71 grams of aluminum per cubic centimeter. And that cubic centimeter, remember, that represents the cell. And it also says that it crystallizes in face-centered cubic. So I know that in face-centered cubic, there are 4 atoms per cell. And I know that the edge is equal to 2 times the square root of 2 times the radius. And that's going to be important because if I can find the size of one edge, I can find the radius out of that equation. Now, something that it doesn't say in the problem, but that we should keep in mind, is that we know that this is aluminum. And so because it's aluminum, we know that the molar mass is 26.98 grams for every 1 mole. That's going to help us convert out of this grams unit from the density. Now, it might be hard to kind of figure out where to start here. So I just kind of want to keep our eye on the prize. What we're trying to find is the radius. So we're trying to find the radius. And because we know this equation, if we're trying to find the radius, we can use the length of an edge to find that radius. Because it is a cubic structure, we know that all the edges of a cube are the same. So if we can find the volume of one cell, we can find the edge because we know that the volume is equal to the length times the width times the height. All those are the same. Those are all edges. And so volume is really an edge cubed. So if we can find the volume, we can take the cube root of it and we can get to the edge. Now I've kind of cleaned that up there to kind of show how we're going to do those steps. If we're trying to get to the volume, and I'm looking at this information over here, where is volume at all? I can see that volume is embedded in the units of density. So I can tell that I'm going to use my density to find volume. But that isn't just a one-step problem. I'm going to use so density is mass over volume. If I have the density and I'm trying to find the volume, I need to know a mass. So I'm going to use my molar mass to help me do that. And remember, molar mass is in units of grams per mole, but I don't want to get the volume of a whole mole. I just want to get the volume of one cell. So I'm going to have to do a conversion for that too. So going from density to the volume of a cell isn't just a one-step thing, but it is something that we can do. All right, now that I kind of have a overall plan here, I'm going to follow it. I'm going to start with the density, and I'm going to kind of do each one of these steps as I go along. This type of problem isn't my favorite problem to do in the world, but as we approach the end of the semester, it is a really good way to practice your problem-solving techniques, your management of information, and kind of your organization, and it's also a really good way to practice your dimensional analysis, getting all those units to cancel out. So I'm going to start with my density. My density was 2.71 grams of aluminum per cubic centimeter, and I'm just going to say of cell. And the reason why I'm being very particular about that is because when aluminum stacks up into a face-centered cubic, not all the space is taken up with aluminum. So this cubic centimeter isn't all pure aluminum filled up by aluminum atoms. There's some empty space in there. And so I'm just trying to be very clear that that is how much space it takes up when it stacks into a face-centered cubic, not how much is filled with atoms. All right, and the first thing that I'm going to do is I'm going to cancel out those gram units, and I'm going to use the molar mass. The molar mass is 26.98 grams of aluminum for 1 mole of aluminum. So it's very satisfying to me to cancel out those units. And then I'm trying to get from moles of aluminum to unit cells. So I'm going to look over here at my information and see what I can do to relate those things to each other. I know that it's face-centered cubic, so there are 4 atoms per cell. So it seems to me that I need to get from moles to atoms, and then I can get from atoms to cells. So to get to moles to atoms, we're going to use a unit we haven't used in a little while, Avogadro's number. 1 mole is 6.02 times 10 to the 23 atoms. And then to get from atoms to cell, I can use the fact that it's face-centered cubic. In face-centered cubic, there are 4 atoms for every 1 cell. All right, let's pay attention to our units as we go along here. Moles would cancel out with moles. Atoms would cancel out with atoms. And what I'm left with is how many cells are in a cubic centimeter. And on my calculator, I actually got that there were 1.51 cells per cubic centimeter. Now, the reason why I'm kind of being a stickler about those units there is when I'm following this path, what I'm trying to find is the volume of one cell. But what I've found is the cells, the number of cells in 1 cubic centimeter. I found the inverse of what I wanted. So if I want to continue on with this plan, what I need to do is I need to take this number and I need to make it into how many cubic centimeters are per cell. That's taking the inverse. So when you take the inverse, you can use a button on your calculator that's 1 over x, like this, or you can just do 1 divided by 1.51, and you'll take that inverse. So what we need to do is we need to take the inverse to get cubic centimeters instead of cells per cubic centimeter. And when I did that on my calculator, I got 6.61 times 10 to the negative 23 cubic centimeters. So that's how much one cell takes up. Now I understand that this kind of idea, taking the inverse, that might make you pretty anxious because you're thinking, how am I going to remember to do that at the end? How do I know that I need to do that at the end? The reasoning there is you're going to know that you need to do it because you need to find cubic centimeters, and what you found was 1 over cubic centimeters, like how many cells per cubic centimeter. So by paying attention to the units, you would know that you need to do this at the end. If you're concerned about like, why did we do it this way so that we have to do this inverse at the end? The reason why we did it is because once you do a lot of these problems, you know that this happens. But if you've never done a problem like this, what we would have had to do is we would have had to start at the very beginning. We would have had to put our density as 1 cubic centimeter per 2.71 grams. So we would have had to flip-flop our density in the very beginning. And most people do not have the intuition to start that way from the very beginning. It's much easier to realize you need to take the inverse here when the units are a little bit more clear than having to take the inverse way up here when you're just starting the problem. So because you guys have been doing dimensional analysis for a while, you've been doing unit analysis for a while, and you're getting a lot of practice, you'll know that when you get to this point and you're trying to find the volume of a cell, when you get 1 over the volume, that's when you need to take the inverse. All right, so we have gotten ourselves to this volume of a cell spot. The rest of this is relatively straightforward. We're going to use the volume to find the edge, and then we're going to use the edge to find the radius. All right, so we know that the volume is 6.61 times 10 to the negative 23rd cubic centimeters, and we know that the volume is the edge cubed. So what we need to do is we need to take the cube root of each side. When we take the cube root of this one, we will get the length of one edge. On my calculator, I got that was 4.04 times 10 to the negative 8 centimeters. The units there, when you take the cube root of something that is cubed, that 3 cancels out, so that's why I'm just getting a centimeter there. That's equal to 1 edge length. And we also know that the edge, because this is a face-centered cubic, the edge is equal to 2 times the square root of 2r. So when you divide both sides by 2 times the square root of 2, you get that r is equal to 1.43 times 10 to the negative 8 centimeters. But the problem asks us for it in picometers, so we need to convert between centimeters and picometers. All right, so a little bit more unit analysis practice. We know that there are 100 centimeters in 1 meter, and we know that 1 meter has 1 times 10 to the 12th picometers. So that comes out to be the radius is 143 picometers. So we got our answer here. But like I said, these problems aren't necessarily the most fascinating of all problems, but they are really good practice for problem solving, critical thinking, organization, and unit analysis, things that we've been practicing over the last couple semesters and certainly this semester. So as we approach the end of this semester, these are the things that you really want to get some practice doing. And these problems are kind of the perfect mixture of those things. So if you'd like more practice doing these problems, there are 3 worksheets that are available to you in our course pack, and all of them have the answers at the bottom of the page. So it's easy to kind of check yourself to see if you're getting the hang of things. So now that we've done the mathy stuff, the rest of our chapter is really about what the difference is between the types of solids. So just to start back at where we did at the beginning of the chapter, we talked about how there were molecular solids, ionic solids, network covalent, and metallic. And then there are these other ones, non-bonding solids. Those are really uncommon. Those are basically gases that don't want to react with anything, but we've gotten them so cold that they've made a solid. Those are really the least common types that we would ever see. So we're going to kind of concentrate on these 4 that are a lot more common. So just to remind you what these solids are made out of, if it's an ionic solid, the crystal is made out of positive and negative ions trying to get close to each other as possible. Our kind of poster child for ionic solids are table salt, which are sodium atoms. Sodium ions and chlorine ions, and they stack up sodium to chlorine like this. And remember, they go in all directions. So there would be a sodium on this side, this side, and there would be a chlorine in between these. So that's kind of our idea of an ionic solid. The next one is molecular, and molecular means that there are covalent bonds within the molecule, and then the molecules themselves are stacked together. Now we say that it could be atoms or molecules because if it's a non-metal, technically it's molecular, and so any pure atoms that are stacked together that are non-metals would be a molecular solid. Now, kind of our poster child for molecular solids would be any molecular compound. So we could talk about water, or we could talk about any, non-metal containing molecule. What I've written here is just a carbon chain. And I just want to remind you that what makes molecular solids stay together, so what attracts the particles in molecular solids, is not like ionic. In ionic, the things that are attracting the compounds are positive and negative. So up here, we were talking about like sodium being attracted to chlorine ions, chloride ions, because one is positive and the other one's negative. In a molecular compound, we don't have that kind of really strong ionic attraction, what we call an ionic bond. In molecular, what we have is intermolecular forces. So in a molecular compound, the things that is holding two molecules together, two of the smallest units, are the intermolecular forces. And those are a lot weaker than ionic bonding. So when we see some data about this, because the intermolecular forces are so much weaker, the attraction between these molecules is so much weaker than an ionic bond, what happens is that these have much higher boiling points and freezing points, and these have lower boiling points and freezing points. All right, so moving on to metallic. In metallic bonding, the smallest units are atoms. They are just, metal atoms that are attracted to each other. And so we'll talk about why that is. And the last one on this list is network. And network compounds, or network covalent compounds, are made up of molecules that have covalent bonds to them. But they're really interesting. They start to have some properties of ionic compounds because of the way that they bond. And just to be clear, what I mean by properties of ionic compounds is they tend to be pretty hard, and they tend to be very crystalline, like have a very clear crystalline structure. But the bonding is different. They just have some of the same properties. So one of the compounds that we see that forms network or network covalent compounds or crystals very often is silicates. And silicates are silicon atoms that are bonded to oxygens. And so that is a covalent bond. That's a bond between two non-metal atoms. But what happens is that they stack up so that another silicon bonds to the same oxygens as that other one was. And then the pattern keeps on repeating. So it's kind of like this is a silicate, and this is a silicate, and this is a silicate, but each one of those is sharing oxygens with another silicate compound. So this is technically all totally covalent, but it has a very rigid structure and a very patterned structure, which is a lot like what we see in ionic compounds. So here we just have kind of a summary slide that gives you the type of solids. It gives you some examples of each one of the solids. It tells you what the smallest unit is, whether it's ions or molecules. It talks to you about the types of forces that are holding the things together. So that's a little reminder that for ionic compounds, it's an ionic bond holding it together. For molecular, it's our intermolecular forces that are holding those molecules together. And on this side, it gives you kind of the properties. And so I want to go through those a little bit, like one at a time. Now, we've talked a lot about ionic compounds. We talked about how they react with each other. We talk about how they react in solution when we do net ionic equations. And so I kind of want to concentrate on these ones that we haven't talked as much about. Okay, so in metallic solids, those are solids that consist entirely of just metal atoms. So the example that I used was an iron stacking up next to another iron like this. And this happens for all our metals. Almost all of our metals are solids. Solids are the most dense state of matter for most compounds. And so that means that the atoms like to be really close to each other. But what is attracting an iron to another iron? They aren't charged, so it's not an electrostatic force like an ionic force. They're not sharing really electrons, like making a bond with each other the way a covalent compound would. So what's holding those things together? To explain this attraction, let's think about some things that we've learned about metals over our 3A, 3B, 1A experience, okay? One of the things that we learn is that when we're doing electron configurations, as you're going along, you fill the S block first, and then you get to the D block. And most of our metals are in the D block. The S block really just doesn't have that many metals. There's just 2 columns there compared to the 10 columns of the D block. So D block metals have more electrons than the S block metals on the same period. And so most of our metals have more electrons than other elements do. Also, we learned that when we were doing electron configurations that there's a lot of movement for those D block electrons. Sometimes the D electrons, sometimes S electrons move into the D shell to give us a half full or totally full shell. So there's a lot of electron movement when you start getting to that D block. There's a lot of different options that the electrons can have. And then one more thing was that when we were talking about periodic trends and we talk about metallic character, one of the things that makes a metal, one of its physical properties, is that it's very conductive. Okay, so our metals are conductive, meaning that electrons can flow through them. So when you put these facts together, what they kind of add up to is that there are a lot of electrons that are moving a lot. Okay, so not only are they moving within the atoms, but they are also moving between the atoms, and that there are a lot of them. And so when we describe metallic bonding, what we've observed is that there are electrons within an atom. Okay, but for the metals, because they have so many electrons and there's electron movement, these electrons kind of flow between the elements, and it makes what we call a sea of electrons. And that sea of electrons, it's almost like instead of the electrons being around one atom, the electrons kind of pool and they are kind of flowing between all the atoms. So that explains our metal's conductivity. That also explains why the atoms stick together. So when we're talking about like covalent bonding, and we're talking about why a hydrogen would bond with an oxygen, it's because they are sharing electrons. That's a covalent bond. And what we're saying now is like these ions are sharing electrons. And so when they share so many electrons and we say that they are delocalized, they're not just around one atom, but they kind of spread out to all the atoms. That's what we call a metallic bond, and that's how we get a metallic solid. Now, it's a very vague or kind of general way to describe metallic bonding. They're just sharing electrons there. Now, depending on how that works out for the element, it gives it kind of a wide range of properties. So if they're able to kind of pool their electrons a lot, those are what we call like really conductive metals. Those are things that tend to be more dense. But if they're not able to do that, they are less dense metals and more likely to be a liquid. So those would be things like mercury. So because we have a lot of metals and there's a lot of flexibility, a lot of options for those electrons, metallic bonds have a wide range of properties. Some metals are soft, like sodium and gallium and mercury. Some metals are really hard and brittle. There's a wide range of properties for metals. Now, molecular solids are held together with intermolecular forces. And depending on how strong those intermolecular forces are, that's what determines the properties of the solid. So if the intermolecular forces are really strong, the solid tends to be more solid. If they're pretty weak, it's a really soft solid. So if something just has dispersion forces or maybe dipole-dipole forces, they tend to be a lot softer and less dense than if they have things like hydrogen bonding. So the way that works out, because they're just intermolecular forces and not actual bonds, most molecular solids tend to be pretty soft, not very dense. They have low to moderate melting points and low to moderate boiling points. They are not good conductors because electrons don't flow between the molecules very well. The electrons really are localized within the molecule and they don't flow from molecule to molecule very much. Some examples of molecular solids would be things like water, So solid water is what we call ice, dry ice, which is carbon dioxide, and any covalent but polar molecule would also be an example. All right, talking about things that are also covalently bonded, but it works out a little bit different, are our network covalents. So sometimes we call them network solids, sometimes we call them network covalent. Those are the same things. Okay. They are, again, made from an array, so like a crystal lattice of covalent bonded molecules. Good examples of those would be things like, diamond. Those are just carbon atoms bonded to other carbon atoms in a crystal structure. Things like quartz, sand, glass. All those things are network covalent solids. All right, and one that wasn't on kind of the original list, but I just want to put in there so that we have something that can contrast these other things too, is this idea of an amorphous solid. Amorphous just means that there's a stacking of something. There isn't a regular pattern. There's no crystal. There's no repeating pattern of any sort. Things are just kind of laid on top of each other. And so when that happens, you don't get like any kind of definite melting point or boiling point. It just kind of starts to melt and then keeps on melting for a wide range of temperatures. So some examples would be glasses that are not silicate glasses. So maybe more reasonable examples would be things like rubbers and plastics. The reason why they're a solid is because to manufacture them, we heat them up, we pour it into a mold, we let it cool down, and it stays in the shape of that mold. But the reason why it keeps its shape is because it's a solid at room temperature and not necessarily because the molecules are really attracted to each other. So those are amorphous solids. Again, they're just kind of like a piling of atoms on top of each other, a piling of molecules. No repeating pattern. Right, so when we take those properties into consideration, what type of bonding or intermolecular forces that are holding compounds together, so ionics down here and metals up here, when we think about those, the types of forces that are holding the solids together, it kind of helps us explain the range in melting points. So metallic bonding, we said that because it's a sharing, like a delocalization of electrons, we get a really wide range of melting points there. Mercury is liquid at room temperature, but tungsten, its melting point is like 3,000 degrees. That's just like a crazy huge range. Most of these other ones don't have quite that range. Molecular solids that are non-polar, so these are only things that have like dispersion forces, they have all really low melting points. What that means is that they are liquids or more likely gases at room temperature. When we're talking about polar molecules, those tend to have a little bit higher average melting point and boiling point because the intermolecular forces are a bit stronger there and they're more likely to be in liquid or solid state, so they have higher melting points. And then ionic solids all have pretty high melting points. So if you think about something like sodium chloride, it melts at 800 degrees Celsius. So that's why if you have like a frying pan and you're cooking and you sprinkle some salt on there, the salt stays in crystalline form. It doesn't like melt into the pan. Ionic compounds just have pretty high melting points because the particles, the ions, are really attracted to each other, and melting means spreading those things apart. So they want to be really close to each other. They want to stay as a solid. So in this chapter, we are talking about the types of solids. We kind of introduced those. We talked about different types of crystal structures, and we talked mostly about the cubic structures. We talked about simple cubic, body-centered, and face-centered. We also talked about, just kind of touched on hexagonal and how that was different in shape. We learned how to do some geometry so that we can use the edge and things like density or the radius to convert between each one. So we can do some calculations with these types of crystals. We also then talked about, kind of came back to the types of solids, and we talked about for each type of solid what the smallest unit was, what the forces holding those smallest units together were, and how that influenced the properties of the solids.